Okay, we're going to talk about a new concept called electric flux. What we're going for is eventually to arrive at a physical concept called Gauss's law. Gauss's law is, you can think of it as an alternative way to calculate an electric field. We've calculated electric fields by integration. We've calculated electric fields by summing up contributions from individual charges, and I should say integration over continuous charges. And as you might have figured out, sometimes that can be fairly cumbersome and somewhat difficult. Gauss's law can represent an easier way to arrive at an electric field, and we can learn a lot of physics from it. But first things first, Gauss's law involves the concept of electric flux. We got to figure out, number one, what is flux? So flux you can think of as the amount of something passing through a certain area. To illustrate what that I have my phone here with a light on, right? I see, you can see the light. Try to convince the screen to go dark here. And what I'm going to do is I'm going to tell you to imagine above this picture of Marty McFly and the flux capacitor that there's an imaginary square outlining this picture. And the reason you're seeing this picture is because light is getting through that imaginary square. Now, I'm going to turn off all my other light sources here and see what happens. So what I'm going to do, and it's going to be a little bit hard for you guys to see, but I'm going to have my phone and I'm going to turn it like this. So that's what you'll be seeing. And it's possible that the screen will come on and I'll have to turn that off, but that's okay. So I'm going to turn off this light source and I'm just going to show you that you can see the picture due to the light on this phone. Sorry, let me make sure I can see what I'm saying. Right, and so clearly there's a couple things I can talk about. If I get closer, the light becomes brighter, right? And this is weird because I'm overexposing the camera, so I'm hoping this is going to work okay on video. If I get farther away, it'll get darker, right? And I'm putting shadows on it. So definitely proximity of the light matters. Now, to understand what I'm going to do here, you have to kind of think of this light coming out from this light bulb as a stream. You can think of it as some sort of vector field. Maybe that works, maybe it doesn't. But you can think of it maybe as a visible electric field coming out of that light. It's definitely not just a visible electric field, but that's to make this analogy work, that's what we're going to think of. Hang on, screen off. So, right. Now, what I'm going to do, right now I have the phone oriented, and I think you can see it, such that the light is shining directly on the picture. But I can turn the phone so that not all of the light is shining directly on the picture. And notice what happens. Oh, come on. The picture gets dimmer as I turn the phone. Why is that? Well, if we're thinking of our paradigm here about this square outlining the picture, if my phone is directed right towards the picture, then all of this light is passing through this imaginary square. But if I tilt my phone, I actually get less and less light passing through this square. Some of it's going over here to the side. Some of it's going up here. Less and less of it is actually passing through the square and striking the picture. And so what happens is the picture becomes dimmer. All right, now what in the world does this have to do? Let me turn on the actual light here. With electric flux. Well, all right. I said that you can think of flux loosely as the amount of stuff passing through a surface. And the example we just saw, let me see if I can draw that. Here is a square. I'm going to have to try to draw this in 3 dimensions. That's not really, that's okay. That'll work. So I have this square and I'm passing light through the square. Now in our analogy, we're going to think about this not as light, but as an electric field. So this square has a certain area, right? And there's an electric field here. So I'm trying to characterize how much of this electric field is passing through this square. Now, what has to make a difference there? Not only the strength of the field, but the area of the square. If I were to just physically make this square bigger, then more electric field could pass through it, right? If I were to make the electric field stronger, then I'd be getting more electric field through it, of course, clearly. Now, this has gotten really jumbled, so let me move up and draw another picture. But also what makes a difference, and this is where my drawing skills are going to be really tested. Let's see if I can draw. The idea is I've taken that square and I've turned it. So in this case, the square is kind of like this. Now I've turned that square and put it in the same field. You see that necessarily less of the field is making it through the square. Right? Up here, when the square was facing, or at least judging by what I've drawn, close to facing the electric field, I get a lot of flux through the square. And there's the first time I've used that word, right? The flux is the amount of the electric field making it through this square. Here, as I turn the square, I get less and less flux. And if I were to turn it completely, like if this is my field and this is my square, right? I get no flux through the square. Incidentally, this is actually why we have seasons here on the Earth. This doesn't have a whole lot to do with electricity and magnetism, but it does illustrate the point. You may or may not know that the Earth's axis, is tilted in relation to its orbit by about 23.5 degrees. And so if this is the Earth, and this is its orbit, and this is its axis, and this is sunlight coming in, right? And here is the equator dividing northern hemisphere from southern hemisphere. Well, look at what's happening. You see that when the sunlight passes through the atmosphere here in the northern hemisphere, the Earth is actually tilted away from the sun. It's not that the Earth is farther away from the sun. You might have heard that. That's actually not, it has very little to do with temperature changes. What does make the difference is that the flux of sunlight through the atmosphere is diminished in the northern hemisphere because it's tilted away from it, and increased in the southern hemisphere because it's tilted towards it. This is when we have winter in the north and summer in the south. We are currently coming into the season that looks like this, right? And if you don't believe me, just go outside. Where here's the equator. We have more direct sunlight coming into the northern hemisphere than the southern, which is why it's getting so darn hot here in Alabama and probably wherever you are also. All right. So the idea is flux. It's the amount of sunlight coming through the atmosphere. Okay, now let's take this back to electricity and magnetism, or at least electricity, and talk about how to mathematically characterize the flux. What we have said is that the flux of an electric field through a surface A depends on strength of E size of A and the angle, and I'm just going to stop with the word angle because we're going to have to be careful with that one. We'll define it rigorously in a second. It depends on the angle that this area, whatever it is, is making with the electric field. There we go. So what I want is a good way to characterize electric flux mathematically. And looking at all this, this actually invites one of what we call the vector products. what is a vector product? We have a dot product, we have a cross product, and I have separate videos on those if you need to brush up or you don't know what I'm talking about, which is totally fine. If you haven't been through Cal 3, you probably don't. But those are different ways of multiplying vectors together. Vector multiplication is not just like scalar multiplication. And both of those multiplicative quantities depend on the angle between the vectors. Now, what's the problem here? Well, the E field's clearly a vector, but area? Well, how can I do something with an area vector? What even is an area vector? So the reason I want to do this is because I know a couple math tricks that would make this easy to characterize. If I could just figure out how to turn this area into a vector, I could do one of my nifty vector multiplications between the E field and the A field. So let me introduce you to the area vector. So here's a square seen from an angle, right? This square has some sort of area. And what I'm going to do is I'm going to draw a vector that is normal to the surface of that square and has a magnitude equal to the area of the square, and the direction I'm going to give is n hat. Remember, an n hat just means a unit vector. The n is going to stand for normal. The idea here is I'm forming a vector that has a magnitude equal to the area of this surface. It doesn't have to be a square, I should point that out. It could be whatever surface element you want, but the magnitude of the area vector is equal to the actual area of that surface, and the direction is normal to the surface. And once I do that, I'm going to just call this guy the area vector, okay, the A vector. Now, I have a way to characterize the E field and the A field. How am I going to do it? Well, okay. What I need is the flux to be maximized. So let me draw another picture. So here's a surface. I drew a square. I'm going to say this is my area vector, A. What I need is the quantity, the flux, to be maximized when the area vector is parallel, sorry, I do know geometry somewhat. What I need is this quantity to be maximized when the area vector and the E field vector are parallel. I need it to be minimized when they are perpendicular. So here's A, here's E. And I said a while ago, if I turn the square flat like this, I get no electric field through it. So I need it to be maximized here. I need it to be minimized here. In other words, if I look at the angle between the area vector and the E field, I need this quantity to be maximized when that angle is 0. I need it to be minimized when that angle is 90 degrees. And the cosine function handles that brilliantly. And when I look at my vector products, that leads me to the that leads me to the dot product. My apologies, the dot product. This is the Greek letter phi, it's the Greek F, it's going to stand for flux. And I'm going to subscript this with an E for electric flux is defined as the E vector dotted into the A vector. You might recognize the cross product here as this magnitude of E, I keep saying cross product, oh my gosh, the dot product, magnitude of E, magnitude of A, times the cosine of the angle between them. Let me say this again because I keep saying the wrong product. Phi sub E is the electric flux. It's the amount of the electric field making it through some surface. That's going to be defined as E vector dot A vector, the dot product. The dot product itself is defined as this: magnitude E, magnitude A, cosine of the angle between E and A. Okay? That is the electric flux. Now, in this course, we're going to use this in just a little bit, in a few videos, to determine the electric field. In other words, we're going to calculate the flux, we're going to find an area, and we're going to get the field out of that. No big deal. What we're going to have to do, though, just to give you the punchline, is we're going to have to integrate over certain areas. We're also going to have to integrate over certain volumes, but that's usually trivial in this case. We are going to have to integrate over certain areas. And so let me remind you of something I alluded to a few videos back. I can take this area, right, where the area vector A, and I'm going to say that this is some x and this is some y. Sure, it could be z, it could be whatever. But what happens if I do my standard calculus trick and I let this x shrink, 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 and I let this y shrink, 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 until they become dx and dy, right? I shrink them down into a differential. What happens to my area vector then? Well, what I used to call A has shrunk to a differential area element, and I now call it dA. And it is still a vector. It is okay for a differential to be a vector. That is not a big deal. But you're going to start seeing this dA, and you might go, well, how in the world does that work? In Cartesian coordinates, it works like this. I take my x and y and I let them both shrink down to differentials. I multiply them together and I get this area element. If I were to write this out, I would say that dA is equal to dx dy n hat, where n hat then is the normal vector to the plane formed by this dx and dy. Okay. Couple of other things to talk about here. We're going to see this in action in a little bit, but I'm going to not take a side step, not take a back step, but just talk about some other things with flux. And so all of the surfaces that I've drawn so far have been open surfaces. That is to say, they're just a surface. They're not a surface that's bounding a volume. But of course, I can draw a surface that bounds a volume, right? There's a sphere. This sphere, of course, has a surface area. It's got a volume, of course, for 4/3 pi r cubed, but it also has an area, 4 pi r cubed. 4 pi r squared. Not cubed, that can't be right. So the surface area of a sphere is one thing, the volume of the sphere is another thing. Now, I want to make the contention that if I put some sort of charge here that's going to be producing an electric field, it certainly appears that there is going to be some sort of flux through this surface, this closed surface. So, to investigate that a little further, we need to think about how we define this area vector. Notice, in this drawing, I could just as easily have defined the area vector like this, right? I drew it going up, but why not draw it going down? And if I'm just dealing with an open surface, that turns out to not be a super critical issue. Of course, anything mathematical is critical, we've got to be careful. But if I'm dealing with an open surface, I can kind of skirt around this issue. But if I'm dealing now with a bounded volume, a surface that bounds a volume, if I'm dealing with that sort of surface, then that all of a sudden becomes pretty critical, right? Because if I'm going to define my area vector as pointing outwards, then this dot product evaluated over here is going to look a little bit different than if I evaluate it on the other side, right? So if I define my area vector as pointing outwards from the volume, everywhere it will look like this. And how I evaluate it on either side is going to be different. It will be different in point of fact by a negative sign. Because over here, you can imagine a field line coming straight through here. Over here, the fields, the field line and the area vector are parallel. Over here, they are anti-parallel. And so over here, I have an angle of 0 degrees. Here, I have an angle of 180 degrees. So you see the evaluation will be different. By convention, and this is just a convention, we're going to define for surfaces such as this, area vector is positive outward. Right? It's just a convention. So we're going to say that this is positive and this is positive. That does not then change the fact that the electric field and the area vector are parallel here and anti-parallel here. This has no effect on that. This is just a convention that we choose. But that in itself, the parallel anti-parallel, leads to some interesting considerations. For instance, notice if I have a parallel anti-parallel situation coming over here, if I put this in some sort of uniform field where the field strength is the same everywhere, and maybe I should draw that to make more sense. The field I drew then was definitely not uniform, but just draw one that's uniform. I'm going to do this one in a ballpoint so it's a little less obtrusive. So there's my uniform field. Let me put in my sphere and show you where the area vectors are in the sphere. These are, what I'm going to say is these aren't just area vectors. I'm going to let any region I can come up with of surface area shrink down to a dA, and I'm going to let all these things be representations of my dA. Right? Or my lots of dAs going around. Of course, if I integrate all over all those dAs, I get A, right? I get the area of the sphere. But I'm going to break it up into little bitty regions and let these things be representative. Of course, there's some coming out of the page, going in the page all over, but I'm not going to try to draw that. They're just way too convoluted. Now, let's look at the area vector here, and it didn't look like I drew it on the other side very well. Look like here there's one pointing outwards. There should be one over here pointing right this way. I didn't draw that very well. All right, okay. Let's look at the flux due to that electric field line right there. I've got E dot dA. Well, over here, I've got, that's going to turn into E dA cosine theta, which is 1, because that's 0 degrees. I should say cosine theta is 1, so I'm going to get an E dA times a 1. Over here, I'm going to get E dA times -1, because that's 180 degrees. And so you see hopefully you see what's going to happen. If this field is uniform, the E dA part is going to be the same on both sides, but it will be a difference in a negative sign. And so integration, remember, is just adding things up. So when I add this E dA to this negative E dA, I get 0. Maybe you can see that's going to happen in pairs all around. This EDA is going to just take off a component here because this is not completely parallel, but there will be an opposite one on the other side which cancels it, and they're going to cancel in pairs as I move around because these things are all directed radially outwards, right? And if the E field is uniform and all the dAs are the same, which of course they are, that's my differential element, then I'm going to get this complete cancellation. And so what is the net electric flux through this closed surface? 0, right? Of course. Now, ask yourself this, doesn't that make sense? If the electric field is coming from outside the sphere, and let me say that again because that's critical. If the electric field is coming from outside the sphere, right, what goes in must come out. Everywhere. What goes in must come out. Fantastic. Now, if the electric field is arising from something inside the sphere, that is different. Here's my sphere. I'm not going to draw the area vectors. Let me put inside that sphere, we'll assume it's like a hollow sphere. I'm going to put inside some charge Q, which is going to produce an electric field, right? Now I have a source of the electric field inside that sphere. The flux through this surface is definitely not 0. But here, because the field is coming externally, the flux through this surface is identically 0. Here, it's definitely not 0. I'm going to actually have to do the integration here. All right, the integration will be done in some examples and some videos, but that's the electric flux in a nutshell.